this
So?
is either or.
So,
If
this is also a linear function, and what happens
because
when
of like
it's zero?
shape.
It's zero.
Okay.
So which line? Yeah, that's a good one. I agree, this was like pretty close.
You switched everything.
You're in the right.
What?
Yeah.
Oh, yeah, so what about
Good.
linear
Okay.
functions?
So you can see where
Yeah,
it
that
is.
one's right.
So
This guy's actually, he looks pretty good, right?
Like,
There's
there's
kind of high.
So he was like,
So this, yeah, if you put it in there here, it actually will be zero. Yeah. So this one's gonna actually start at four. Okay, so which line maybe is that one?
Why?
Yeah, that's a good guess. Why did you think that was not points?
Like,
Yeah, so it's not this one, it's actually this one. Excellent.
and I was like, I love your help right now. And like, you can't.
Yeah, and then I mean, this one's kind of tricky because it just was maybe
No,
okay,
because
cool.
like,
So
if you
linear
like
functions
a
are
big
done. Now you can move on to like quadratic functions.
Oh.
This looks good.
when you get to the water, so
I think about like
but
physics
you're
where
like,
what other one would be
Yeah, but like-
so then grab a part of the
Say that. Like, if I had to choose like chemistry,
Yeah, now it's gonna go like
I could
for sure right now, I'm just bare feet, I'm thinking,
It's 12 for G, and then, alright, here we go. H
And you can
is
test some other things too, like if you want zero, you should add zero.
H is A7.
Start order.
A7.
How are you doing?
I is A5.
H is A7.
H is A7. And then I is A5.
J is A6.
Wait, so this is
J
just,
is A9.
yeah, this is just a workshop. And then, so I guess I'm not sure what you need.
But
What about?
I enjoyed
You said
it.
L
Oh,
is
you,
A8.
oh, I totally understand, yeah, and I have to go in my roster, so, okay. So you're just, enjoyed a function activity and now you're leaving.
As it goes higher and higher, it's like a slow exponential.
I think it's
So we'll take like breaks and lunch or whatever, and we're just, this is just prep for. Yeah, so I don't know what
Remember the number from the A, the lower it is,
So there's
the
the
higher
count,
the
there's a
problem.
different one that has all the counting.
Sean, is this, in my head, I just, you know how it is, so I just thought I could.
Are you, so are you part of the STEM
Yeah.
school?
I'm good.
Oh, okay, so this is just for workshops for the people in your class. So I don't know, yeah, I mean that you won't be on any of the rosters.
I'm not gonna get any
So
sleep.
I guess technically,
I'm gonna sleep on it.
technically this workshop is not for you.
Like, Mondays and Wednesdays, like come in at 7, but then Tuesdays and Thursdays, I guess it's 5. And, yeah,
I'm actually gonna have, that's like my job.
So, yeah, so, yeah, so 27, and I think it's last year, we actually started with this. Yeah, I think that might have been the started last year. So you might be looking at activity.
Do you guys have,
Yeah, and they're not good about updating stuff either, so, okay.
All
right, well,
No, they're really good. Like, I really.
Yeah.
Like, nothing, sorry, I'm just like,
Like, the way he comes in and he came over here.
oh, so Mondays, yes, you start or
Kevin?
Yeah, this is
no,
like
there is a chem class, no, there.
Yeah, there's a chem workshop, but I think he's just talking about chem class,
Oh,
yeah. Yeah, I agree,
You
there
could
you
go,
go.
yeah, no, you're
I
ready.
would.
Yeah, no, just show up to the chem line.
So
There
you
you
just make
go.
the right and go straight where the food's at, and then you should.
Are you telling me to put it on?
Yeah.
It's gonna be in our office, she's gonna be over there.
Do you check?
Probably shoes right here.
Do you get any offers for?
Alright, so shall we talk about some of these? Are there any that we just felt like, yeah, I totally know this one, I'm not, yes,
The Ferris wheel one.
the Ferris wheel one, which function is it?
It's a sign.
It's sine. Okay, so I think we all felt good, right? Sine is one of these functions. We'll do a little trig review later in the week, but if right now you're like, yep, sine, it oscillates back and forth, and it also has to do, I think, maybe I heard some people talking about this over here, it's related to circle, right? Like sine and cosine are these values we get from the circle, and so, like, that's really what's going on. We're like going around a circle. Okay, cool. So we can check that one off the list. Were there other ones that we felt like, yeah, I think this one is relatively clear?
B.
Okay, so B, what did you think, Valerie?
So for B, I did A4, which is y equals to negative x plus 100. For me, this felt like pretty reasonable because there's a total distance, and then so you're moving from town A to town B, which means that you're taking away the distance. So that means that the x would be negative, and then if the ultimate is 100, then depending where you are, you're going to be towards the 100 or not. So if you move away from the x as you add more, you're going to be moving towards the b, so then it will decrease but also increase.
Yeah, so then what does the 100 kind of represent?
The total amount of distance.
Yeah, so this 100 is really like how far apart these two towns are, and this is what's happening here. And we also see like, yeah, as Valerie was saying, the negative here is telling us like we have this negative slope. Okay. Did you have a different one, Pedro? Or?
Well, I had the same, but I could go.
Yeah, so which one?
A, the plumber one.
Alright, so what did you think for the plumber one?
The graph is G2, so I put the equation A3, which is y equals 40x plus 60.
Yeah, okay, so this is the one where we kind of started off here and got bigger. And what were you thinking for this one?
Well, I felt like all of those numbers made sense. And all
Yeah.
of that made sense because first off, he has an original amount that is the original payment, no matter how much is there.
Yeah, the like original fee, huh? And then what does the 40 represent?
The 40 is how much he charges per hour. The rate.
Okay. Yeah, and then it totally does match up with like, what kind of function is this?
Okay, it's a linear function.
It's a linear function, and it's got a positive slope and a positive intercept, so we know we're like up on the y-axis and we're increasing. Great. Any questions about this one? All right. What other ones are we?
We can move to C.
C. Okay.
So it says that, well, I chose the equation A1, which is y equals to 5x minus 10. So obviously, like at one point you watch the first movie and the second movie, so that's going to be in the negative, which is fine because if you put the numbers in, it'll be a negative number, so you can put it in the end. So that's why it's
Yeah, so those are like here.
the 0 and the 1. So 0 would be negative 10, 1 is at negative 5. And then it fits in with the rest of them.
Right, and then as we fit in more dots, we're getting more. Up here. And again, maybe this is one where you think like, oh, I would have some kind of piecewise function. Maybe and say for these ones I'd actually make them be 0. But in any case, we see that it is like the 5 maybe is representing like how much it costs per movie after the first 2, and then when we plug in 2, we see it really was free. Okay. That sounds good. What else?
I mean, that, well, I was like technically you can put parameters in there, but that's not what we're going to do. Because that would like make it to be what it is, like in the picture, because then you put like x, like boundaries, you know what I mean?
Yeah, that you would maybe say like for x being 2 or more, it works, but when x is like 0 or 1, you would just, or 2, we'd make it 0. Yeah, I agree, like this one maybe could use some modification, but like the base function you'd be using, I agree, is 5x minus 10. Did you have a hand up from one you wanted to share?
Yeah, sure. It's for L. Oh, I got 1/4 x squared.
Okay, so L, the film projector problem, we said it's one of these curvy problems, and why did you arrive at 1/4 x squared?
The projector, like you said, it can never be 0 to a screen there at some point.
So I guess this one is like, when I plug in 0, I guess I do get 0, but that's okay. It looks kind of like half of, like what kind of function is
Half
an
of a problem.
Yeah, this looks a lot like half of a parabola, and this is a parabolic or quadratic function, gives us parabolas. So we've got half of this parabola. So do you guys remember when we were kind of talking about like what was the difference between the exponential and the parabola? Like those shapes look really similar. But why should this one be x squared and not, you know, an exponential function? So maybe I'll just say something briefly about like when you project on this screen here, maybe if you were thinking about like projecting as forming this kind of square picture, every step you take back, you'd be increasing by some amount x how wide and how tall the picture is. So the area, it should be some kind of quadratic or squared function, because how do you get the area of this projected image? Well, it's just x times x. And then there's like some scaling amount, which is that maybe it's not telling you that exactly at 1 foot we're like 1 by 1, we're like 1/4 by 1/4. But the point is here that as we step away, the area of this is growing, and area is coming from a quadratic value, not an exponential value. Does this make sense? Any questions about this one? How about some, yeah.
I did for test drive of the car.
Yeah, the test drive.
I chose A5, y is equal to 200 over x.
Okay, so this is the test drive. It looks very much like this. Y equals 200 over x. So can you elaborate a little?
I chose that equation because that's what I'm doing the asymptote on the y-axis. And then that means that x will, at 0, y does not exist.
Yeah, so when x is 0, we can't do that because we can't divide by 0. So you're exactly right. It won't exist here. And then what's happening the other direction?
It's slowly getting closer to 0, but I don't think it will ever touch 0.
That's right. So you're saying like here, when I move this direction, I'm plugging larger and larger values in for x. So maybe in terms of like an idea from calculus, if I'm plugging bigger and bigger values in for x,
It's getting really small.
it's getting infinitely smaller, and maybe I'm even saying something like, well, the limit as x goes to infinity of this function is actually going to 0. We'll do some limit refresher in a bit, but this might be a way of saying what you were saying there in terms of an idea from calculus. Questions? All right. What about the paper folding problem?
I did y equal to 2 to the power of x over 1,000 because it's an exponential growth one. So that means that x has to be taken to a power. That's what I kind of did now. And then I don't know if the numbers actually have to do with these, but because it was that way, I did it by 2.
Yeah, okay, no, I think that that's exactly right. So you're saying for the paper folding, we were saying like for every time we fold the paper, like if I fold it 1 time, I'm getting twice the thickness. And if I'm folding it 2 times, I'm getting another twice, so we have 4 times the thickness and so on. And then maybe this 1 over 1,000 part, like where are we divided by that? Well, the paper is really, really thin, right? So maybe the paper is like 1/1000th of an inch, and then I multiply by more and more 2's to say I'm doubling how thick that is. What do we think about that? Does that seem? How about, what about the kettle cooling problem? So did anybody have an answer they felt like good about? Yeah.
I have an answer, but I don't know that.
Okay, we'll share it, and then I'm sure that we can all help one another out.
So for that one, I chose y is equal to 20 plus 80 times 0.27.
So you're 20 plus 80.
I could try it, see why I chose that.
Yeah, please do.
So first I saw that it was a 20, so it starts at a fixed temperature, even if it was to be 0. So I started off like that. And then I saw that even though it has an exponent, when you multiply it, or when you make the exponent, the x factor bigger, it won't get bigger, it will get smaller. So I saw that since it's adding that, it's like slowly decreasing.
Okay, so this point, I'm gonna say this out loud for everyone one more time. So you're just saying, if I put in some bigger numbers for x, I'm not actually getting bigger values. And why is that?
It's a decimal that you're.
Okay, so this decimal, so this 0.27, this is a number that's smaller than 1. Right, and so when I have really tiny numbers and they start multiplying them together, I actually get smaller and smaller numbers. So it's not always the case that just like putting in bigger exponents makes my value bigger. So this is a perfect example of a type of problem where, maybe you recognize that property, or maybe you just plug in a couple of values of x and you see that it actually is making that get smaller and smaller. But ultimately, as we, well, actually we should be a little bit careful here. So I didn't mean to write a 20 there. What happens when we plug 0 in for x?
Becomes a 1.
This becomes a 1, so we actually have 80 plus 20. So I guess we've got 100. What's the 20 actually going to represent for us?
Just always, it's gonna be above 20 no matter what.
It's going to be above 20, so maybe I could put the 20 down here and say that I'm going to approach the value of 20. So let's think, this problem was about like a kettle with temperature cooling. Can we say anything about what these numbers actually represent?
The 100 that's a boiling point of water, so.
Right, so what units are we secretly using here?
Fahrenheit.
Celsius.
Celsius.
Celsius, yeah, okay. So degrees Celsius, 100 degrees Celsius is boiling point, and if we were doing Fahrenheit, I guess this would have been like 212.
Yeah.
Questions about this? So do we agree then that this is the right function to use? Yeah, I do. I think this is great. So what we just witnessed, perchance, the paper folding problem, this was an exponential that was getting bigger. This is also an exponential. This is an exponential function, but it's just one where the value is getting smaller. So don't always think that exponentials always look like, e to the x where it gets bigger. If we have a base that's smaller than 1, we're going to see the exponential going the other way. Did you have a question?
Yeah, so when there's temperature problems, should we assume at all, like if it's exponential, if it's something along those lines, or no?
So there are a variety of cooling problems that you might run into, and most of them do involve this kind of some factor, some base that's for exponential. But in general, I would say that you won't see so many temperature problems in Calc 3, but you will definitely see exponential functions where your base is smaller than 1 or where your base is bigger than 1, and being able to distinguish between those in general will be important. How about the balloon problem? Or the height of the golf shot? Yeah. What are you thinking back there?
I was thinking speed of the golf shot.
Okay, great. Speed of the golf shot. Which one are you thinking?
H.
H. So which?
10 square root of x minus 3 to the power 2 plus 7.
Okay, so this one I think was probably pretty tricky. Like maybe when you looked at this one, I don't know that any of us felt, I will include myself in this any of us, that felt that when we look at this function, we're like, oh yeah, I definitely know what that graph looks like. I think that's kind of tough. So let's maybe talk through a little bit, why should it look like this? So I don't know, can you give us an idea of something that you were thinking?
So on the y-axis, the little dots, I counted 7, and in the equation it says that it has to be starting at a height of 7.
So when we plug in, like I agree, there's this plus 7 that's maybe kind of like shifting some stuff up.
Yeah.
When we plug in 0, kind of happening?
It's still gonna be, a value, so you know it won't be touching.
Yeah, so it's gonna be something like way up here, right? It's gonna be 10 times the square root of 9 plus 7, which is 16, so I guess really this is up at 40. I think the hash marks are kind of like just there.
The thing that gives it away is what's in the parentheses. So once you hit 3, it's going to be 0 inside, which means it hits the lowest point and then starts climbing back up.
Good catch. All right, so here, like when we plug in 0, we're getting 9 squared plus 7, and if we plug in, like I guess 6, it's going to give us the exact same value, right? Because negative 3 squared is the same as positive 3 squared, so those are the same heights. But we just saw that if we plug in 3, this part's going to be 0, and that's going to be the smallest spot we can be at. So this is in fact a graph that's decreasing and then increasing again. Questions about that? This is not one, I will say, if you are feeling at all apprehensive, this is not a graph that anyone's going to expect you to be able to sketch with any accuracy, but just this kind of matching idea is enough. So what do we, I guess maybe do we feel okay with the internet cafe one? We didn't really do that one, but it's just a linear function. The 3/4 x. What's that? Do we want to talk about that one? We can. Okay. So it's another linear function, and it's got a positive slope of 3/4. But our last two, so maybe let's do some thinking about kind of parabolic things. The height of the golf shot. It's a parabola, right? But what direction is the parabola opening?
Down, so it would be the negative.
Yeah, so when we've got a parabola that's opening downward, we know that means that the coefficient, I forgot.
30.
Thank you, 30x minus 5x squared. So this is the negative coefficient on the x squared is saying this is a parabola that opens downward. And that might be enough for you to be like, sure, it's this guy. Another thing to notice though, I guess, is like, what is this 30x doing? Like if I didn't have this 30x, where should this parabola be living?
At the center. Well, I think.
Yeah, like it should be opening around the y-axis maybe. But I guess it would be like down here.
Yeah.
So this 30x is actually shifting. It's actually shifting the parabola. And so this is how we end up with it looking like this. Like, I guess maybe other things to notice is like what happens when I plug x equals 0 in? I actually get 0. There's no constant term here, so it should actually be down here. And then I notice that it's a parabola, and there's going to be like the point of the vertex. And to really see, I guess, why it's this shape, you might do something fancy like complete the square. But suffice it to say that if you have a parabola where you have just shifted by some amount and you've got a negative coefficient, you just have a parabola that's been shifted over and you're opening. I guess another thing maybe that could help see is like if you see a term like this and you're kind of like, I don't know, what's something I could do with this? I guess you could factor a common term out. Like what's a way we could rewrite this by factoring something out? 6x minus x squared if I factored out the 5. What's another common term I could factor out? Yes, okay, great. So then I would have 6 minus x times 5x. So I think from here you can kind of see like plugging in x equals 0, we already knew it was 0. What other number would we maybe plug in for x and get a 0? 6. So where is that on this graph?
At the end.
At the end. So this point here, 6, and then middle 3. And if you plug that in, you'll see that that's the biggest value. But something that is often useful here is if you had multiple intercepts that you were thinking about for your graph, you can figure them out algebraically. Okay, the very last one maybe to say something about is the balloon problem. So process of elimination, which function is our balloon problem? 5/4 bigger numbers, it's gonna get bigger. If I plug in 0, where am I? The origin. Why is it like a curve and not a line? Because it's, okay, so it's, I know what you're thinking. You're thinking the exponent is not 1, but I guess we would say this is like a power function. So one way you could write it, I suppose, is as x to the 1/3. So you're just like really emphasizing it's not a line, it's not linear, it's got a different power on the x. What's a reason why we would be seeing like cubed roots? Why would we have a cubed root? What is this what's the problem about? What was like the physical stuff? There's a volume. So if I'm thinking about volume, so I would have like a cubic maybe. So when we were doing like the area problem, we saw like an x squared showing up. So a volume problem would maybe have like an x cubed. But the way that we're using, which variable is the volume? In terms of the x or the y in this problem? The x was giving us the volume, right? So in some ways, that might be backwards, where like when you're thinking about volume, you would have like, if x is the volume, you'd have some kind of, and I'm not saying it's exactly y cubed, because there's some other factor here. But if I were to solve this for y, if x is y cubed, what is y equal to? The cubed root of x. And so we're not being super precise about the actual volume of this balloon, but the point is that volume is a cubic thing. And so when we were kind of thinking, well, x was actually our volume, so it was a little bit backwards and we solved, that's why we're getting this cubed root. So things to watch out for is if like your problem involves area, you might be looking for a squared thing or a square root thing. And if your problem involves volume, you might be looking for a cubed function or a cube root function. Those are things. Okay, how are we doing? Do we need to take a mental break for a couple minutes? Or do we want to just push through and then go to lunch early?
Let's do that.
Let's do that. Okay. So I want to change gears now and start getting into calculus. Like I've given us maybe like a little taste. Oh yeah, you can put all of this stuff, and it doesn't matter who organizes it, back in the little baggies. But just to kind of get back into calculus, we have three main topics that you saw in your Calc 1 class. The first one that you probably talked about were limits. Yes? We've heard this before. The second one that you used limits to define and then did a whole bunch of problems with, derivatives. Great. And then, after you use derivatives for a bunch of application problems or whatnot, you moved into the topic of integrals. So just to get back into calculus ideas, because I'm going to tell you, whomever you take Calc 3 from, they're going to expect that you have a familiarity and even can solve lots of problems with limits, derivatives, and integrals. So we're going to be sure to get you all ready with all these topics. But to get back into it, just talk with your neighbor. What did you remember? What were the point of these things? What notation showed up? Just anything. You're just getting juices flowing. So just chat with neighbor, and then we'll collect answers as a group.
For a long run, because I was always just, I don't know, it was like a whole thing in my head, but now I have a better understanding of it, and just figuring out where the aspects of stuff so I just used them to know they were relevant to what I was doing, and then I figured out they weren't, because then once you get into other derivatives, I a lot of integral. Okay, I really think I want to do but I'm way better. And it's okay. And then we used to talk about I understand the use, but I still don't.
And these are really good. So we know what in the area for the curve. Like this is it's just
Okay, we're very quiet. Would we rather talk as a whole class? All right, let's do it. So, and it doesn't really matter what order we talk about these things in. So somebody share an idea about one of them. What's a thing you remember? Yeah.
For derivatives, wasn't it d over dx?
Okay, so like a notation that you might use is if you see something d over dx, this is the derivative, I guess we would say operator, like you would see d over dx and you would apply it to a function, right? And that would mean take the derivative of this function with respect to the variable x. What's another notation that you guys might have seen for derivative? Like the derivative of f of x. Okay, like f prime. So maybe you might think something like, these actually mean the same thing, right? F prime of x means I've taken the derivative of f with respect to x. And this is kind of the thing that's telling you, I'm going to do it. I'm going to take the derivative. Okay. What are other things you remember? Maybe about, I don't know, about derivatives. Like, what is it?
Like the power rule.
Okay, so like so power rule, that's the thing we know about derivatives. How does that work, Valerie?
Can I make up a function?
Sure.
Okay, so like x cubed plus x squared.
Okay, so you're saying let's do the derivative of this function.
So that would be 3x squared
3x squared
plus 2x.
plus 2x.
So I'm not going to do the plus 0.
Yeah, okay, so then you're saying, like, maybe I'll put it in parentheses.
Yeah.
Plus 0 because the derivative of 1. So each one of these, like this, the derivative of a constant is 0. Each one of these, you are doing the power rule of that portion. And then we know that when we do derivatives of things that we're adding, it's great. It's like you just take the derivative of each piece and add them together. And so in general, when we're talking about the power rule for derivatives, the derivative of x to the n is just n times x to the n minus 1. Okay. So that's a good one. What other things do we know?
I know the quotient and product rule, but I feel like it's for the integral, the uv plus uv or v prime u.
Yeah, so I guess, so you're right, the quotient, we've got product rule and quotient rule are actually derivative rules. And maybe I'll leave these for just the time being. Maybe not write all of them out, but we might talk about them a little bit later. What is a derivative? Like, what does it measure in terms of a concept or a geometric thing?
Isn't it like the critical numbers, like in a function?
Okay, so we use derivatives to find those critical values, to find like maxes and mins. Like we looked for where the derivative is 0. And like, why are we even doing that for maxes and mins? Like what? Like maybe show me just a shape that would give you a maximum. Like yeah, like a parabola. Like you might go up and then you come down. And so the derivative at that maximum is 0 because it's measuring the slope of something. Does this sound familiar? The slope of
Tangent.
the tangent line. Or another way you might have heard this is the derivative is measuring a rate of change. Does this sound familiar? Derivative is a rate of change. So this idea will come up when anytime you are doing a problem where they're asking you about slopes, where they're asking you about how fast things are changing. These are all derivative problems. Okay. So in general, I think, like, do we feel okay mostly about computing? Maybe let's just say at least simple-ish derivatives. We'll practice some this afternoon, but we have the right idea about, we know what derivative is. All right, what topic should we talk about next? Limits. All right, so what's a thing you think about when you think of a limit?
The notation or like recursive LIM, X, and an arrow or
Yeah, so you might write like, the limit as x goes to 3, I don't know, like x plus 1 over x. Who cares? I can take limits of functions, x approaches some value, and I'm gonna maybe go out on a limb and say limits may actually be our least favorite of these three. Is this true? Maybe not. I don't know. So yeah, I think people have a tough time with the concept of a limit because you guys are not actually given a very nice definition of limit. Like what's the whole thing about limit?
So as x approaches a number.
As x approaches a number. So is it really as x equals this number?
No.
No. Yeah, it's not. So like maybe I'll stick a slightly more interesting one up here. Like, I think a lot of times the way that we